Good day, esteemed researchers and curious minds tuning in from around the globe. We're here to delve into Galactica, a large language model for science, a groundbreaking study that reimagines how we interact with scientific knowledge. This research challenges the traditional store and retrieve paradigm, proposing a novel approach using language models as powerful tools for exploring literature and scientific knowledge. Stay tuned as we unravel how Galactica disrupts the status quo and opens up exciting new possibilities in the realm of scientific inquiry. We're entering a new era where language models could revolutionize how we access scientific knowledge. Instead of the traditional store and retrieve paradigm, which heavily depends on human effort, we're exploring how language models can serve as a more efficient interface. Now let's talk about the current methods and their limitations. Incorporating new knowledge often involves retraining models from scratch or from older checkpoints, a process that can be resource-intensive. For more specific knowledge, we use retrieval augmentation. But here's where our proposed method comes in. Language models have shown an impressive ability to absorb technical knowledge and compose a curated knowledge base. They've demonstrated strong performance in knowledge-intensive question-answering tasks. This could be the key to unlocking a new way of exploring the vast body of scientific knowledge. In our research, we utilized a variety of datasets, including PubChem compound, UniProt, and RefSec genome. These datasets allowed us to explore the potential of language models in absorbing and utilizing vast amounts of scientific knowledge. We also applied data augmentation techniques to the document format to enhance the learning process. Our evaluation focused on two main tasks: citation prediction and knowledge-intensive question answering. The results were promising, demonstrating the potential of language models in these areas. This suggests that language models could be a valuable tool for exploring scientific literature and knowledge in the future. For over half a century, we've been accessing scientific knowledge through a store and retrieve paradigm. This method, while effective, heavily relies on human effort to reason, combine, and organize information. As a result, we face a significant bottleneck in knowledge throughput. The image here illustrates the multimodal data we're dealing with. Our challenge is to find a way to disrupt this paradigm and create a more efficient interface for humanity to interact with knowledge. We propose a transformative solution: language models. These models have the potential to disrupt the traditional store and retrieve paradigm. They can absorb vast amounts of scientific knowledge and perform impressively in knowledge-intensive question-answering tasks. However, there are challenges to overcome. The current paradigm has limitations, requiring continual learning and verification, which can be time-consuming and resource-intensive. The importance of addressing these challenges cannot be overstated. The current bottleneck in the field is the availability of high-quality, step-by-step datasets. Language models can help us overcome this bottleneck, opening up new possibilities for the advancement of scientific knowledge. A key improvement in our research is the introduction of the working memory token approach. This approach has shown to significantly enhance performance on mathematical MMLU and math benchmarks. But the potential of this approach goes beyond mathematics. It enables language models to act as a bridge between scientific modalities and natural language. This means that complex scientific concepts can be translated into understandable language, making knowledge more accessible. This is a significant step forward in the field of language models and opens up exciting possibilities for future research. Our research proposes a novel approach to knowledge exploration, utilizing language models to delve into scientific literature. These models are not just readers, but active learners, absorbing complex technical knowledge, including LaTeX equations and chemical reactions. But they don't stop at learning. They also compose, creating a curated knowledge base that can be used to answer knowledge-intensive questions. This is achieved through a unique working memory token approach which has shown strong performance on mathematical MMLU and math benchmarks. Now, let's delve a bit deeper into the methodology. We envision language models as a new interface for interacting with knowledge. These models are trained to absorb vast amounts of scientific knowledge, transforming them into a flexible and accessible format. Moreover, they are trained to compose a curated knowledge base, providing a structured and organized platform for knowledge retrieval. The working memory token approach is a key component of this, enabling the models to perform strongly on various benchmarks. In essence, we're not just using language models to read and understand scientific literature, but to actively learn, organize, and apply this knowledge. In our research, we've designed experiments using datasets such as PubChem compound, UniProt, and RefSeq genome. We've applied data augmentation to the document format to enhance the learning process. The performance of our model was evaluated on tasks like citation prediction and question answering, showing promising results. Now let's talk about the improvements and innovations we've made. We propose a new approach to accessing scientific knowledge, moving away from the traditional store and retrieve paradigm. Our work demonstrates that language models can absorb large bodies of knowledge, including technical details like LaTeX equations and chemical reactions. But we didn't stop there. We've also shown that language models can bridge scientific modalities and natural language. This opens up exciting possibilities for tasks like automatic protein annotation and drug discovery. In essence, we're exploring how language models can become a new interface for humanity to interact with knowledge. Our research has yielded some key results that we're excited to share. We've found that language models can absorb technical knowledge, including LaTeX equations and chemical reactions, which is a significant step forward. In citation prediction, these models outperformed both sparse and dense retrieval pipelines, demonstrating their potential in this area. We've also made strides in mathematical benchmarks, such as MMLU and math, by using a working memory token approach. This approach, illustrated in the figure, allows the model to perform exact steps for rearranging an equation, offloading complex calculations to a classical computer when needed. Furthermore, we've seen how these models can compose a curated knowledge base for knowledge-intensive question-answering tasks. This is a promising development for the future of information retrieval. Lastly, our research has shown the potential of language models to act as a bridge between scientific modalities and natural language. This opens up exciting possibilities for the integration of diverse scientific fields. Our research indicates that language models have the potential to revolutionize the way we access scientific knowledge. Instead of the traditional store and retrieve paradigm, these models can absorb and organize technical knowledge, such as LaTeX equations and chemical reactions, with impressive efficiency. This capability opens up new avenues for exploring literature and scientific knowledge. We've also found that language models can excel in knowledge-intensive tasks. For instance, our working memory token approach has shown promising results on mathematical benchmarks like MMLU and math. This suggests that tasks previously thought to be exclusive to human specialists could be solvable with language model approaches. Furthermore, our initial investigations reveal that language models can bridge the gap between scientific modalities and natural language. This opens up exciting possibilities for tasks that are currently human specialisms. In essence, we're looking at a future where language models could become an integral part of our knowledge exploration and scientific discovery process. We've embarked on a new approach to accessing scientific knowledge, disrupting the traditional store and retrieve paradigm. Instead, we're harnessing the power of language models as robust absorbers of technical knowledge, from LaTeX equations to chemical reactions. When it comes to performance, these language models are not just keeping pace, they're leading the way. They outperform existing methods in citation prediction and excel in knowledge-intensive question-answering tasks. But we're not stopping there. We see a future where these models take on tasks that are currently performed by human specialists. In essence, we're on the brink of a revolution in how we interface with knowledge, and language models are at the forefront of this exciting journey. Language models have shown great potential in bridging the gap between scientific modalities and natural language. This has been demonstrated through tasks such as IUPAC naming and molecule net, where language models have been able to learn and perform effectively. However, we also face challenges. One of the key bottlenecks is the availability of high-quality, step-by-step datasets. To overcome this, we've introduced a working memory token approach, which has shown strong performance on benchmarks such as MMLU and math. This approach allows language models to perform complex tasks in a step-by-step reasoning manner, similar to how humans would approach these tasks.